안녕하세요. 로데 슈바르즈 코리아의 최지홍입니다. 예, 이번에도 저희 웨비나로 여러분께 돌아왔습니다. 다시 한번 여러분 참석해주신 여러분께 만나서 반갑습니다. 인사를 드립니다. 예, 오늘 지금 바로 내일 모레면 우리 민족의 대명절인 추석이 시작됩니다. 바로 그 앞에 이제 저희 준비를 해가지고요. 또 여러분들 바쁘신 와중에 또 이렇게 참석을 해주셔가지고 정말 감사를 드립니다. 오늘 저희 준비한 내용들은 그 디임베딩이라고 하는 주제를 놓고 벡터 네트워크 분석기와 연관된 내용들로 말씀을 드리려고 준비를 했습니다. 오늘 내용 설명을 위해서 저희 로데 슈바르즈 코리아에서 기술 지원으로 근무하고 계시는 이재현 매니저님을 여기 함께 모셨습니다. 매니저님 인사해 주시죠.
네, 안녕하세요. 저는 로데 슈바르즈 코리아에서 벡터 네트워크 분석기 제품과 관련 어플리케이션의 기술 지원을 담당하고 있는 이재현 매니저입니다. 제가 이번 톡IT에서는 웨비나는 2번째 진행하는 것 같고요. 만나 뵙게 돼서 다시 한번 반갑습니다.
예, 오늘 이재현 매니저님과 함께 벡터 네트워크 분석기 그리고 디임베딩에 관련된 주제로 여러분들께 1시간 동안 말씀을 드리게 될 것 같습니다. 오늘 준비된 내용은 저희 로데 슈바르즈에서 글로벌로 진행한 웨비나를 저희가 자막 처리해서 여러분께 함께 보여드리는 내용이고요. 관련된 내용으로 현장에서 여러분들께서 질문 올려주신 내용에 맞춰서 또 저희가 바로바로 그 설명을 드리고 또 어떤 내용들이 우리가 실제 업무에서 적용할 수 있는지 이런 부분들 중심으로 해서 여러분들께 또 답변을 드릴 수 있지 않을까 이렇게 생각이 됩니다. 이재현 매니저님, 오늘 주제가 벡터 네트워크 분석기 그리고 디임베딩이라고 말씀을 드렸는데 이 벡터 네트워크 분석기 도대체 어떤 건지 먼저 좀 한번 설명을 부탁드릴 수 있을까요?
네. 주신 질문에 앞서서 먼저 이번 웨비나에서 어떤 게 진행되는지 먼저 말씀을 드리고
예, 좋습니다.
그 다음에 차례로 말씀드리는 게 좋을 것 같아서요. 우선 이번에 웨비나에서 소개드릴 내용은 크게 압축해서 2가지 정도로 말씀드릴 수가 있을 것 같습니다. 첫 번째는 올바른 프로브의 선택이고요. 저희가 오늘 같이 소개드릴 웨비나에서 말씀드릴 내용이나 솔루션에 적용할 수 있는 측정 대상이라고 한다면 보통 PCB라든가 혹은 SOC 테스트를 할 수 있는 테스트 보드나 혹은 일반 테스트 픽처가 될 수가 있는데요. 이런 측정 대상을 프로브를 가지고 측정하실 때 어떤 고려하셔야 되는 다양한 조건들이 있습니다. 그래서 이런 조건들을 어떤 것들을 고려하셔야 되는지에 대한 내용이 첫 번째 주제고요. 두 번째 주제는 이러한 픽처에 대한 특성화할 수 있는 방법입니다. 예를 들어서 저희가 측정 대상, 어떤 PCB를 프로브로 측정한다 라고 했을 때 측정 결과를 보시면 내가 원하는 측정 대상만의 측정 결과가 있는 것 뿐만 아니라 거기에 내가 사용한 프로브의 특성도 같이 포함이 되어 있습니다. 그렇기 때문에 결론적으로는 이 프로브의 특성화를 정확하게 해서 나중에 디임베딩이라는 기능을 이용해서 최종 결과에서 이 프로브의 특성만 빼주는 그런 절차가 필요한데요.
그러면 이게 측정 결과를 정말 순수하게 측정 결과만을 얻기 위한 방법이다 이렇게 생각할 수 있을까요?
네, 맞습니다. 디임베딩 같은 경우에는 요즘에는 이 측정 대상들이 PCB나 이런 것들은 콕셜 커넥터 타입이 아닌 것들도 굉장히 많이 있기 때문에 그런 것들은 어쩔 수 없이 테스트 픽처라는 거를 사용하거나 별도 테스트 보드를 사용하십니다. 네, 그런 것들은 결론적으로 콕셜 커넥터 타입 끝단까지는 캘리브레이션이라는 과정을 할 수가 없기 때문에 정확한 DUT만의 특성을 위해서는 디임베딩이라는 별도 테크닉을 통해서 이런 것들을 제거해주는 기능이 있고요. 그래서 이런 더 나아가서 응용 분야로 프로브 자체도 프로브를 특성화를 해서 그 프로브의 역량을 결론적으로 측정 결과에서 제거해주는 그런 방법을 두 번째 주제로 말씀드릴 거고요. 더 나아가서 이 두 번째 주제에는 프로브를 이용해서 측정하실 때 결론적으로는 프로브가 테스트 보드에 접촉이 될 때 접촉되는 부분에서 내가 원치 않는 불연 속성이 발생을 하게 됩니다. 그래서 특성화한 프로브의 특성뿐만 아니라 최종 결과에서 프로브와 프로브의 프로빙으로 인해서 발생하는 불연 속성까지 같이 디임베딩 해주는 그런 솔루션을 같이 웨비나에서 말씀드릴 예정입니다.
이거 설명을 쭉 들었습니다만은 일단 제가 듣는 입장에서는 뭔가 양자역학 같은 느낌이 드는 것 같아요. 그 양자역학에서 제가 기억하기로는 관찰을 하기 위해 접근해서 개입하는 것 자체가 결과를 흐트러뜨린다. 뭐 이런 얘기를 제가 들은 적이 있는 것 같은데 이 디임베딩이라고 하는 내용이 그런 오류를 막겠다라는 개념, 뭐 사실 양자역학에 쓴다라고 말씀드리는 건 아닙니다만은 뭐 그런 식의 어떤 컨셉적인 부분이 비슷한 게 있어 보인다. 뭐 이 정도가 일단 제가 받은 느낌인데 좀 더 자세한 내용들은 뭐 동영상에서 다시 한번 또 내용을 통해서 보실 수 있으실 것 같고요. 그러면 오늘 준비한 주제는 뭐 그런 얘기들을 하게 될 거고, 그러면 여기에서 지금 오늘 주인공은 사실 어떻게 보면 그 네트워크 분석기라고 하는 장비가 될 것 같은데,
네, 맞습니다.
이 네트워크 분석기가 어떤 일을 하는 장비인지 간단하게 좀 설명을 부탁드릴 수 있을까요?
네, 지금 앞서 말씀드린 두 가지 내용은 어떻게 보면 네트워크 분석기를 이용해서 응용할 수 있는 분야에 대한 소개라고 볼 수가 있고요. 기본적으로 네트워크 분석기는 뭐 전통적으로는 RF 분야에서는 뭐 종사하신 분들은 굉장히 많이 들어보시거나 사용해 보셨을 것 같습니다. 기본적으로는 RF 소자, 예를 들면 뭐 필터라든가 혹은 앰프, 뭐 안테나와 같은 그런 컴포넌트들의 특성을 측정하는 장비인데요. 최근에는 이 PCB나 혹은 뭐 SoC 테스트도 마찬가지로 고속 통신을 좀 커버해야 되는 케이스가 많다 보니까 고주파까지 측정해야 되는 케이스를 네트워크 분석기라는 제품을 가지고 측정을 하고 계신다고 보시면 되고요. 그래서 이번에 말씀드릴 좀 포커스는 여기서 측정 대상은 이제 별도 뭐 이런 RF 소자라기보다는 PCB나 뭐 보드와 같은 것들이 되겠습니다.
제 기억으로는 저희 로데 슈바르즈 코리아가 9월에 그 전시회에 참가를 했었습니다. 그 KPCAshow'라고 하는 전시회에서 저희가 그 저희 솔루션을 전시를 했었는데, 그 당시에 제 기억으로는 저희가 전시했던 솔루션이 벡터 네트워크 분석기와 프로브 스테이션 뭐 이런 제품들을 저희가 솔루션으로 전시를 했던 기억이 나는데, 그 솔루션에 해당되는 부분들이 오늘 이 발표되는 주제와 어떤 연결성이 있는 내용일까요?
네, 오늘 웨비나에서 소개될 측정 예시들하고 셋업을 보실 수가 있을 텐데요. 이 셋업과 동일한 것이 네, 전시회에서 같이 전시가 됐었고요. 간략하게만 말씀드리면 67기가, 70기가까지 측정 가능한 디퍼런셜 프로브와 저희 67기가 네트워크 분석기와 같이 연동을 해서 프로브를 디임베딩 해주는 이런 솔루션을 뒤에서 보시겠지만 그대로 전시를 한 경험이 있습니다.
만약에 오늘 참석해 주신 분들 중에서 전시회에서 저희 부스를 방문해 주셨던 분이 계시다면 아마 어쩌면은 또 그때 보셨던 내용들을 또 리마인드 하실 수 있는 그런 기회가 되지 않을까 하는 생각도 들긴 합니다. 예. 지금 시간이 지금 약 7분 정도 지났는데요. 오늘 준비된 내용이 약 한 50분 정도 되는 것 같습니다. 그래서 지금부터는 여러분들께 저희 글로벌 웨비나를 통해서 저희가 말씀드렸던 내용들을 한번 쭉 같이 보시면서 내용들을 보시고요. 또 그 과정에서 여러분들 그 질문 있으신 분들께서는 이 채팅창을 통해서 바로 올려주시면 저희가 동영상 끝난 후에 한꺼번에 저희가 그 답변을 드릴 수 있도록 그렇게 준비를 해보겠습니다. 지금부터는 여러분들 함께 동영상으로 웨비나를 내용을 함께 보시겠습니다.
Hello and welcome to our webinar about accurate measurement with differential probes on high-speed signal structures. We're doing this webinar together with DVT Solutions, and we will talk particularly about two different aspects. On the one hand, the selection of the right probe, and on the other hand, the characterization of the probe so that you can properly de-embed that from the measurement result. My name is Martin Stumpf. I'm segment manager in Rohde & Schwarz for high-speed digital test, and I'm joined today by Brian Shoemaker, President DVT Solutions, and Greg Ward, Product Planner, Vector Network Analyzers in Rohde & Schwarz. We have prepared three different parts today. In the first part, I will give you an introduction into the topic, and I will particularly introduce the concept of test fixture characterization and de-embedding. In the second part, Brian Shoemaker will give an introduction into probes and the various aspects and details about probes. And in the third part, Greg Ward will share some measurements. He will guide us through the measurement process and particularly share tips and tricks about how to make most accurate de-embedding measurements with probes. This is a setup that we are using throughout the webinar. It includes, on the one hand, a Rohde & Schwarz Vector Network Analyzer CNA, the CNA 67, and on the other hand, a test board That test board on one side is connected with a probe, a differential DVT 70 gigahertz probe, and on the other side it is connected directly with coaxial cables. Let's get started. This is a very typical scenario that we see in the industry. We have a signal channel between two SoCs, an SoC on the left side, an SoC on the right side. And what we want to measure and what we want to characterize is the signal structure between the pad underneath the SoC on the left side and the pad underneath the SoC on the right side. Typically, this measurement is done without the SoCs, using differential probes. So the probe would connect on the left side, where you normally would have the SoC, and it connects on the right side, where you normally would have the other SoC. Obviously, what that means is the measurement results includes the differential probes. That means the differential probes need to be characterized and removed so that you can later only get the result of the actual signal structure. A second example is actually a test board that is used for characterizing an SoC. For instance, characterizing with an oscilloscope, an AWG or a BERT. Obviously, we cannot connect these instruments directly to the SoC. We have coaxial connectors. We have a lead-in between the coaxial connectors and the SoC. And also this lead-in needs to be characterized. Why? Because this lead-in needs to be de-embedded from the scope, AWG and BERT results, so that we get the measurement results of the SoC directly at the SoC and not just at the coaxial connector. How do we do it? Again, we use a differential probe typically. We do the measurement without the SoC, connect the differential probe to the pads where the SoC would be connected, and measure the trace between the differential probe and the coaxial connector. Also here, the measurement result will include also the differential probe. Also here, the differential probe needs to be characterized and de-embedded so that the result will be the characteristic of the lead-in, and that can be imported as a touchstone file to the scope, the AWG, or the BERT. As this is a quite common requirement in the industry, Rohde & Schwarz has introduced a so-called de-embedding assistant. This is a workflow implementation in the Rohde & Schwarz vector network analyzers CNA, CNB, CNBT, and CND. And what it actually does is it guides the user through this workflow. In a first step, you would characterize the topology. And in the first step of this characterization, you would select the type of the DUT. In this case, we have a DUT with a differential, a balanced input, and a balanced output. This is what you see here. In the second sub-step of this, you would need to characterize the lead-in and the lead-out. Here, we have chosen a balanced lead-in and a balanced lead-out. In the second step, you now do the measurements. First is the measurement of the 2x through, and second is the measurement of the total structure. Once you have done all the measurements, you hit the apply button, and you would then do the calculation of the fixture models. You would de-embed them from the measurement result so that the result that you are getting is the result, in our case, without the probes. How does it work? De-embedding, and particularly we are talking about impedance-corrected de-embedding, uses two structures. The one structure is the total structure consisting of a lead-in, the DUT, and the lead-out. And the second structure that is being used is normally a reference structure. Quite often we use a 2x through, but other structures are also available, like a 1x open, like a 1x short. And the way how we construct the 2x through is actually we build in this 2x through a replica, a replica of the lead-in. This is what you see here, a replica of the lead-in. And on the other side, you have a replica of the lead-out. What is important to notice is that these are replicas. They are not the lead-ins and the lead-outs themselves. They are just replicas. And as such, these replicas never have exactly the same impedance profile as you would have on the actual lead-ins and the actual lead-outs. And that means it is very important to do impedance-corrected de-embedding. Traditional 2x through de-embedding didn't do that. Traditional 2x through de-embedding just took the models from the 2x through coupon and did not use the total structure. The problem with this is that the impedance profiles of these replicas are different to the impedance profiles of the actual lead-ins and lead-outs, and that causes phantom limbs, that causes measurement inaccuracies, and that is the reason why impedance-corrected de-embedding has been introduced. With impedance-corrected de-embedding, you're getting a lead-in model, which is exactly matching in terms of the impedance profile the actual lead-in, and you are getting a lead-out model, which is exactly matching in terms of the impedance profile the lead-out. With these two models, you can mathematically remove, that means de-embed the lead-ins and the lead-outs, and you get an accurate measurement result of the DUT without any phantom limbs on the lead-in side and the lead-out side. Now, what does it mean for our example where we are measuring probes? I'm showing here a screenshot from our vector network analyzer, actually showing the TDR, the impedance profile, looking into the differential probe. The first thing that we are seeing here is the discontinuity on the input of the probe. This is the connector. Then we are going through the probe, and then we see a very big discontinuity. And this is actually the discontinuity that comes from the touch point where the probe pins are touching the board. Certainly, this discontinuity is not related to the signal structure that we are measuring. This is just related to the fact that the probe is contacting the PCB. Then, if we look into the next stages, we see the actual trace that we want to measure, and we see the last discontinuity, that is the coaxial connector. So what does it mean for us? Certainly the discontinuity where the probe touches the board, this is not part of the trace that we want to measure. And that means we want to shift the reference plane from the probe tips into the structure so that we are getting past this discontinuity. This also explains two more things. On the one hand, this discontinuity is very much dependent on the actual board and the way how we are making this probe connection. And that means that you need to have impedance-corrected de-embedding because this discontinuity will be different between the actual board that you are measuring and the reference structure, for instance, a 2x through. And it also will be different to anything that a probe manufacturer has when delivering factory-made de-embedding files. So you cannot really use factory-made de-embedding files for accurate results, and B, you need impedance-corrected de-embedding for maximum accuracy. This basically means, as a conclusion, for accurately characterizing probes so that you can accurately and completely remove them from the measurement results, you need on the one hand to measure the total structure. And on the other hand, you need a reference structure. And as a reference structure, we have two choices. Choice number one is basically to use a 2x through. With this 2x through, we need to have an additional board with a very short trace. This short trace will give us a reference plane that is slightly shifted compared to the probe pads. And the other alternative is to use a 1x open and a 1x short. With the 1x open, you would leave the probe pins open. And with the 1x short, you would short the probe tips. With this, you are getting a reference plane right at the probe tips. And as we discussed earlier, you need to shift this reference plane from the probe tips a little bit into the structure. And this is what this parameter flight time scaling is about. With this, I would like to hand over to Brian Shoemaker to give us some more details about probes.
For the past 17 years, many hundreds of signal integrity engineers have been using our differential probes to make time and frequency domain measurements on differential traces designed into the final product form using time domain reflectometers or vector network analyzers. I'm going to provide a short history on why the first differential probe was developed and how the differential probe internal architecture has replaced the traditional interconnecting wires with a patented high bandwidth printed circuit board, the DVT FPP70 70 GHz differential probe. We'll look at the architecture of the probe and compare it to the dual wafer probe, which has been around since the 1980s. Both types have their strengths and weaknesses that benefit the measurement ecosystem when they're used appropriately. We will touch on what S-parameter measurements are stored in the VNA touchtone file, what the electric characteristics are for both types of probes, and the kind of applications where true differential probes are best used. You will see a DVT Solutions desktop probing system and its components for horizontal and vertical probing. I will list a few takeaways for you and provide you with my contact information. In 2005, we introduced the DVT 30 gigaprobes, the world's first true differential probe with no ground, a variable pitch probe, and plated with conductive diamonds to cut through any surface oxide in order to ensure repeatable, accurate measurements. Figure 1 is a sample of a differential measurement using this probe. In 2011, we collaborated with Signal Microwave, American Probe, and Global Circuits Innovative and introduced the new DVT40 40 GHz differential probe at the DesignCon 2011 symposium. It also has the same variable pitch and conductive diamond plating. You can create differential and single-ended time domain impedance measurements and differential S-parameter measurements to 40 GHz with De-Embedding applied. Figure 2 shows a time domain plot where the green insertion loss S-parameter is the accumulation of the frequency loss from the differential probe and the trace loss measurement. When the ISD DVT40 probe model is used in the VNA, the blue trace shows the probe loss is removed from the trace measurement when De-Embedding is applied. Figure 3 shows the differential and single-ended impedance measurement captured using the DVT40 probe. By 2019, the industry demand for higher data rates over differential traces necessitated higher bandwidth differential probes. DVT Solutions, in partnership with Signal Microwave, introduced our patented fixed-pitch differential probes up to 70 GHz. In 2020, we added differential de-embedding using the Ataytech In-Situ De-Embedding ISD software, which complements the probe's hardware design through the creation of a probe model for the differential probe. A VNA uses the resulting probe model to de-embed the probe loss from the differential trace measurement and applies an algorithm that improves the probe's hardware performance and models the differential crosstalk, therefore eliminating the need for a physical ground. Our true differential probes have no amplifiers but have passive interconnects that are functionally equivalent with the differential trace found on most printed circuit boards as seen in Figure 4. The remainder of the presentation focuses specifically on the new patented DVT FFP70 70 GHz true differential probe as seen in Figure 5. This probe does not contain wires, but a printed circuit board with differential 70 GHz trace conductors. Being a true differential trace, it does not require a ground probe to probe wide-pitched traces centering around 1 mm with a 70 GHz bandwidth. When a probe is used with the VNA to acquire S parameters from a differential trace, differential and dual probes acquire different sets of S parameters. So, it is important to know which probe to use for a particular measurement application. A dual wafer probe is made up of two 50-ohm wires, each wire having a ground and a signal pin at the probe tips. This probe measures a full complement of 16 single-ended S parameters, stored in a touchstone file by the VNA, as shown in Figure 7. A differential probe is optimized to measure odd-mode differential S parameters so that the VNA only acquires single-ended insertion and return loss and coupling S parameters. To view meaningful data, these single-ended S parameters must be converted to mixed-mode differential to view the SDD21, SDD11 differential insertion and return loss S parameters as shown in Figure 6. So now we're going to contrast the electrical characteristics of wafer probes available since the 1980s with the differential probe introduced in 2005, available from DVT Solutions and their sales representatives. A probe electrical characteristics are the most important thing to consider when choosing a probe. First, determine if the probe has enough bandwidth for your measurement and whether the bandwidth specification is maintained when the probe tips match the spacing of the test pads on your board. For example, if you need a 70 GHz probe to match the 1 mm test pads on your board, you must have a 1 mm probe pitch. The fundamental probe architecture of a dual wafer probe is two 50-ohm cables, and most manufacturers specify these probes as 50-ohm probes. However, they do not have electrical coupling between the two signal conductors and therefore are not true differential probes. The obvious key specification when selecting a probe to measure differential S parameters is getting a probe that can probe the same test pad pitches as the trace you need to probe. Now, the typical test pad pitch range for board probing is between 0.8 mm to 1.2 mm, or it could be a little smaller. You need to select a probe to match the test pad pitch setting at the specific bandwidth for the measurement. But if you look at a wafer probe datasheet, they usually only provide measurements for the probe bandwidth with the probe spacing between 50 micron to 250 micron. We understand from reviewing datasheets from several wafer probe manufacturers that provide a probe pitch to bandwidth specification with a probe pitch of 1000 micron or 1 mm, you can drop the probe bandwidth by 60%. Our differential probes are designed to measure wide pitch test pads, and the bandwidth specifications found on the datasheet is measured with a 1 mm pitch probe. A differential probe is ideal for characterizing differential traces on a printed circuit board. Differential probes are used to make time and frequency domain measurements of the final prototype printed circuit board product form against design specifications using visual analysis. The DVT FFP70 70 GHz probe could be used to characterize 56 GHz Nyquist S parameters for PAM4 220 gigabits encoding designs. Figure 9 illustrates using a VNA to probe a device test board and applying De-Embedding to reset the VNA measurement point to measure return loss on the transceiver outputs while the chip is active. In Figure 10, we remove the semiconductor device from its characterization board, use a VNA and a differential probe to create a De-Embedding file from the device transceiver pads to the RF connectors, reattach the device to the test board, connect a digital oscilloscope, and apply power. Load the De-Embedding file into the digital oscilloscope to move the measurement to the I/O pads, thus eliminating the differential trace loss from the active measurements in the oscilloscope. All differential and non-differential probes can be connected to our modular desktop probing systems. The picture illustration is an example of a dual probe system to make time and frequency measurements for probing horizontally of a prototype of the final product design. The probe system can be configured to probe most any size test board. The individual components can be stored in a cabinet in between a design verification. To perform front-side and back-side vertical probing, add one of these variable vertical test fixtures to your horizontal probing system to probe both horizontal and vertical test boards. Finally, let's review features common to all differential probes. Their rugged, wide-pitch probe design allows us to probe printed circuit boards. Bandwidth specifications are measured at a 1 millimeter pitch. They're a true balanced differential probe, no ground probe required, and it contains two signal-to-signal conductors and acquires differential S parameters STD21 and STD11 and stored as a touchstone file. We use the Atayatech ISD software to de-embed the probe and to solve difficult measurement applications for our customers. Thank you for listening to our story about the development of our differential probes. And again, my name is Brian Shoemaker from DVT Solutions. Please contact us if we can be of assistance. Greg will now show how to create a probe de-embedding file for our 70 GHz differential probe with the Rohde & Schwarz ZNA 67 GHz vector network analyzer.
Thanks, Brian, for these insights. With this, I would like to hand over to my colleague Greg Ward. Greg will show us some practical measurements, and he will particularly guide us through all the steps that are needed to get best and most accurate measurement results.
Hi, this is Greg Vaught from Rohde & Schwarz. Welcome to this video, which is a collaboration between Rohde & Schwarz and DVT Solutions. DVT Solutions has supplied a 70 GHz differential probe to be measured with the Rohde & Schwarz ZNA 67 vector network analyzer. Let's take a quick look at our measurement setup. So we've got ports 1 and 3 of our ZNA vector network analyzer connected here to our differential probe. That's the DVT FFP70, which is a 70 gigahertz differential probe from GigaProbes. And you can see we've got this XYZ positioner to get it positioned exactly as we need on the board. And we can also use this flexible camera, which connects over USB, to get a really close look and make sure we're connecting our probes exactly as we need to. This test board we have has a couple of features that are very useful for this demonstration. There is a small copper pad which you can use to short the probe tips together. So that's what we need to do for our 1x short test coupon when we do our de-embedding. And then very close to that are two landing pads for the probes, which are connected to a differential transmission line. And then we split off into two 1.85 millimeter connectors. Those go back to ports 2 and 4 of our ZNA vector network analyzer. So this differential transmission line is essentially our DUT, and our goal is to create a model for this probe that we can de-embed from the measurement so that we're just left with the transmission line. So let's get started by getting our ZNA 67 set up to make our differential probe measurements. So we have a start frequency of 10 megahertz and a stop frequency of 67 gigahertz. Notice we are fully calibrated all the way in this range. If we look at our sweep setup, we have a frequency step size of 10 megahertz, which gives us 6,700 sweep points over the range. The reason I have it set up this way is I want to set up what's called a harmonic grid. A harmonic grid is essentially a start frequency and a step frequency being the same value. In this case, it's 10 megahertz. The importance of this is later on, we want to do a step response calculation into the time domain, and we must have a harmonic grid in order to perform that calculation. First thing is I want to set in our balanced port configuration our differential setup. So we have a predefined selection which maps ports 1 and 3 to differential port 1 and ports 2 and 4 to differential port 2. So I'll say OK. Notice we now went from single-ended S11 to differential STD11. And I'm not really connected to anything now, so we're not really measuring anything at the moment. I want to add a couple more traces before we get started. So I'm going to take my quick add trace button from the toolbar. STD11 is fine for now. I'll do one more. And I'll make a couple changes here. I'm going to change the format of this one in the upper right to phase. And I'm going to put a marker 10 megahertz. I'll explain why in a second that I'm doing that. And down here, I want to make this a time domain measurement. So we can go, well, first let's set our format to be real. Then we can go into our time domain menu. Make this a step response. With the step response, we need a DC value. We can let the analyzer extrapolate down to DC so we get an accurate value. And then let's turn this on. So now you can see we have time domain in our x-axis. You can make that whatever you want. For example, 10 nanoseconds, whatever you need to do, you can zoom in. And the reason I want to see step response here in the beginning is because when we do our test coupon measurements, which are 1x open and 1x short, this makes it easy to see what's going on as far as when our probe touches down and when it's not. So when we have an open circuit, we will have a step response of our reflection coefficient at a value of +1, so I could put a marker on there. And when we get a short, which is required for our 1x short test coupon, we should see a -1 value or approximately thereof. So that's the reason I'm going to start with this step response measurement. And I think we are ready to go to start making measurements with our probes. Here I'm going to show how you can get the data for 1x open and 1x short with the probes. The idea is for the 1x open, we're going to leave the probe tips sufficiently away from the board so that we can get the 1x open, and then we will move them down in position to touch the board, and you can see this close-up view of the camera that there's a shorting bar on our test board. So we want to put the probes into position on the shorting bar to get our 1x short. And then both these files we can use later with our De-Embedding assistant. So right now, as you can see, the probes are sufficiently raised away from the board. So here's where we could export a data file for 1x open that we can use later to import into our De-Embedding assistant. And really quickly, notice we're looking at all the reflection measurements. So in the upper right corner, we have the phase of SDD11, and it is at roughly 0 degrees at 10 megahertz, which is our closest point down to DC. And then notice on the bottom, we've got our step response. So with the step response in the time domain, we're going to have a +1 when we have an open, and then it will shift to -1 when we get a short. So we're going to keep an eye on those two metrics as I lower the probe tips down to touch the board to get our 1x short. So I'll start moving the tips down. We appear to have made contact. We'll get it a second to see if we have, and we do not quite have a change in the measurement. Let's go a little further. Give it a second to update. And you can see here now we have shifted to a -1 step response on the bottom in the time domain. And then on the top, you can see the upper right, our phase has now shifted to approximately 180 degrees at our low frequency marker. So now we could export this data. This would be our 1x short, which we can also import into our De-Embedding assistant later. Okay, now we're going to show the process of touching down on our test points. So you can see now we've moved the probe in position above the two test points, which are connected to a differential trace. And the key measurements to look at here, we have SDD21. So we are going to look for that to be close to 0 dB, down in the 10 megahertz range. And also at the bottom, we are going to want to see our step response in the time domain change from the open circuit that we see now to something more like a smooth transition, somewhat close to 0, so that we don't have a lot of reflection. So I will start to move the probes down into position, and we'll just monitor our measurements along with the camera. I'll let the measurement update really quickly. So we now have what we're looking for. So now you can see on our SDD21 trace, we have almost no loss at 10 megahertz as we expect. And our step response down at the bottom has shown that we went from a step response of about 1 for the open circuit to much closer to 0 as we look through the time domain, as we look down the structure. So this gives us an indication that we now have a good touchdown. And that means we're ready to go into the De-Embedding Assistant to start de-embedding the probe. Now that we have our probes into position, I just want to make one quick change on our measurements. I want to switch this bottom time domain measurement to show us impedance in the time domain. Before it was showing the step response of the reflection coefficient. So now you can see we're centered around 100 ohms as we expect, 100 ohm differential impedance. Let's change the scale to 120 ohms at the top and 80 ohms at the bottom to zoom in a little bit. And this gives us a good idea of what we're seeing. So we are calibrated to the ends of our test board cables. And so this first discontinuity we see in impedance is from where we connect into the probe with our cables. This goes through the differential probe, and then this is the area where it touches down onto the board. Then this is the differential trace on the board, and then this last reflection is the connector launches, which go to the from the board to the 1.85 millimeter connectors. So this area here is actually our device under test, and we just want to de-embed this part because this is the probe and the touchdown area. So this impedance first in the time domain does a good job of showing us everything that's going on with our DUT and our probe. So let's now go into our De-Embedding Assistant and start de-embedding. So in our De-Embedding Assistant, we have different fixture tools that we can use. So you can see we have ISD, SFD, and EZD. In this demonstration, we're going to use the ISD fixture tool. And the first part of the De-Embedding Assistant is to set up the structure of the device under test. So we have the differential transmission line, so that's a 1-by-1 balanced structure. And then how do we want to model our fixture? Now we actually only want to model the left side because we've got the probe on one side. We don't need to do anything on the right side. So we can actually go into our ISD advanced settings and tell it we don't need to do anything on the right, so we can skip the ports on the right. No model needed there. Most of the other settings in here are default, and the one other thing that we can do is we can check on the DC extrapolation. So that just means our fixture models will be modeled all the way down to DC. Sometimes that's handy if you want to take the fixture models and use them into other instrumentation, like an oscilloscope that might need a DC point included in the fixture model. So we'll close that, and now we'll move into our next. And this is where we define what is our test coupon. And we have different options here. We've got symmetric 2x through, 1x open, 1x short. And in this case, we're going to do 1x open and 1x short. So as I showed previously, we put the probes into open and short positions, and we could save those as files. So we can actually go and select those. So I'll select the 1x open file, and then I'll select the 1x short file. Alternately, you can define the ports and measure them, the open and short. But I saved some time by saving those as S2P files earlier. So that's our 1x open, 1x short coupon. And then we're going to do an impedance corrected measurement. So that is the state we are in now, where we have our probes touch down, and we want to make a measurement of the probe and our device under test, which is the differential transmission line. So we're going to get a measurement of that. And then once we have this measurement, we've got everything we need to make a model of our probe. So we've got the test coupon data, and now we've got the fixture, which is our probe, plus DUT measurement. So now we can just hit apply, and this is where our fixture tool, which is the IST tool, is going to generate a model that we can de-embed from our measurement. Now the fixture tool has completed, and we have our model. And if we check our de-embedding engine, we can see that we have an S4P file representing the model of our left side of our DUT, which is essentially the probe. So we are now actively de-embedding that. So let's take a look at our results. So first off, let's save all these traces to memory. And then we can turn de-embedding off, and we can basically see what happened with the de-embedding. So let's give it a second to update. Okay, so now we have a comparison of de-embedded and traces that are not de-embedded. So first of all, in insertion loss, this is what we expect. Our red trace is not de-embedded, but our black trace is, so you can see there's definitely less insertion loss. That's because the insertion loss from the probe has been removed from our measurement. But when we look at return loss, the de-embedded result is the purple, and definitely the blue looks better. So what is going on there? Did we not get an accurate model of the probe? Well, I would say the model is just a little incomplete, and we can get a good view of that in the time domain. So in the time domain, you can see that as I mentioned before, this is our device under test, and you can see the blue trace, which is the de-embedded trace, essentially has the DUT, but it also has part of where the trace touches down on those pads. And so we are getting discontinuity from the pads, the impedance of the probes touching down on the board itself. That's all still in our measurement. And the reason is our test coupons went to the edge of the probes, so they do not include anything from where it touches down on the board and going away from the probes. So we actually didn't remove everything that we wanted to from the board, from the probe. And so what we want to do is find a way to get rid of this part as well and see how that impacts our return loss. To help us figure out how to remove this part here where the probe is touching down on the board, I'm just going to make a couple marker measurements. So first thing, I'm going to get rid of this memory trace, and then I'm going to save this trace which is not de-embedded. I'm going to save that to memory, and I'm going to put a couple markers on here. So let's put a reference marker at 0 seconds. And marker 1 can be a delta marker. I'm going to position it right in the area where we want to model up to. So this is still parts that we want to de-embed, because this is where the probe is touching down on the board. And then everything out here is the device under test that we want to actually measure. Okay. So next thing I'm going to do is I'm going to pull our probe away from the board, because that'll show us the electrical length of the open circuit. And remember, the 1x open coupon sort of defines the electrical length and essentially how far into the structure do we model our probe so that we can de-embed it. So I'll lift the probes away from the board. And you can see I can put another marker up here, marker 2. So if you look at the green trace, that shows us where the open circuit stops. That's somewhere in here. So you can see it's about in the 557 picosecond range. but we actually want to model further out, maybe into the 630 or so picosecond range. So if you do the math, that means we need to do about maybe 10 more percent so that we are de-embedding further into our structure. So that's something that we're going to try on our second iteration of de-embedding. As you can see, I've moved the probes back into position. And so that exercise just gave us a good feel for how much additional modeling into our structure we need to do. So I can delete this memory trace again here and gets rid of all the markers. So let's go back and do this one more time. So we'll go into our de-embedding assistant. We're going to make one change. Remember, we want to do about 10 more percent. So I'm going to put 1.1 for my scaling factor. So this is a really handy setting in our ISD advanced settings. It allows us to do modeling further into the structure. So I will close that. Everything else will pretty much be the same, so we don't need to make any changes here. We'll load our open and our short data that we took earlier. We'll make our Pro plus DUT measurement. And then hit apply to generate our model. Okay, we have our new model. And you can see in our de-embedding engine, we've got our test fixture model for the probe. So we're de-embedding that. And these memory traces are from our first iteration of de-embedding. So let's delete those. And then let's save our current results into memory. And then turn de-embedding off so we can get a comparison. So we'll turn de-embedding off. So the insertion loss is a very similar story as our first iteration. We have less insertion loss from de-embedding the fixture up here. So we saw that already. But now our de-embedded return loss is a much better story here. So you can see it sort of tracks the results of no de-embedding at low frequencies, but then at high frequencies, we really see the effect of removing the probe completely from the measurement. And then in the time domain, you can see here the blue trace. So we can turn this off for a second. So the blue trace is our de-embedded trace. So we no longer see those really sharp discontinuities or steps from where the probe is touching the board. So we're really just measuring the differential transmission line, which is our DUT. And then we can turn this back on. This is the part with no de-embedding. So we are getting rid of everything, the effect on the probe, all the way up to this point here. So that's what we did in our second iteration by changing that scaling factor. So that gives us a really nice result for our return loss, and our insertion loss is also accurate now that we've de-embedded the probe. The final thing that I would like to do is to perform a consistency check on our differential probe model so that we have confidence that our model is accurate. Now, this consistency check is recommended by the IEEE 370 document, which is a document concerned with de-embedding test fixtures accurately. And the consistency check is as follows. We want to plot the time domain step response impedance of two different structures. One of them is the actual structure itself with no de-embedding. So that would be our differential probe all the way through the test board. Then the second structure that we want to plot the time domain impedance is our actual fixture model. And we plot them together on the same scale as we're shown here. So the green trace is our fixture model and the pinkish trace is our actual structure. And notice that for the length of the fixture model, the impedance overlaps pretty much perfectly the real structure. So that gives us a lot of confidence that we have a very accurate model. And notice that we are modeling all the way into this area when the impedance starts to settle down. And the first iteration we did, remember, our model stopped somewhere in this range. So we were able to extend it with our scaling factor for the lead-in to give us all the way through the probe touchdown of the board so that we can model all of that and then de-embed it so that we are just left with the part that we're concerned with, our device under test. So I would say this consistency check that we did here gives us a lot of confidence that we successfully are modeling our differential probe plus the touchdown onto the board. So we can be confident in the results that we get once we do our de-embedding. So that concludes our demonstration of modeling our differential probe. Just a quick summary of what we did. We did an open and a short with our probes so that we could use those as 1x open and 1x short test coupons for our de-embedding. We did 2 iterations of de-embedding. After the first iteration, we found that we needed to go further into our structure so that we could remove the touchdown on the board discontinuity. Once we did that, we did our consistency check to make sure that we have an accurate model, and we did, so we can successfully de-embed our probe and measure only our DUT accurately.
Thanks a lot to Greg, and also thanks a lot to Brian. We are now here at the end of this webinar. I hope it was useful for you. I hope you got a couple of key takeaways from this webinar. Last but not least, I would like to share a few links. On the one hand, the link to our General Rohde & Schwarz webpage, and on the other hand, a reference to an application note that we have recently introduced, an application note about accurate test fixture characterization and de-embedding. With this, I would like to say thank you and have a nice day.
네, 지금까지 저희 로데 슈바르즈에서 진행했던 글로벌 웨비나 내용들을 자막으로 함께 내용들을 쭉 보셨습니다. 그리고 저희 자막 작업을 하면서 저희도 좀 생각보다 어려운 내용인가 하는 생각이 들었었는데요. 일단 뭐 내용을 쭉 보셨기 때문에 이제 아마 좀 더 디임베딩과 이 디퍼런셜 프로브, 네트워크 분석기 이런 쪽에 대한 내용들을 조금 더 아실 수 있는 어떤 좋은 기회가 아니었나 하고 생각이 됩니다. 이재현 매니저님, 오늘 그 발표된 내용들 먼저 한번 간단하게 정리 좀 부탁드릴 수 있을까요?
네, 오늘 소개해드린 웨비나 내용을 앞서 말씀드린 2가지 주제 측면에서 좀 정리를 해보자면, 첫 번째 주제는 올바른 프로브의 선택에 관련된 주제였습니다. 그래서 결론적으로는 프로브는 뭐 주파수 범위라든가 혹은 내가 측정하고자 하는 PCB의 시그널이나 그라운드의 형태, 혹은 피치 사이즈, 혹은 뭐 TDR이나 S 파라미터와 같은 측정 목적에 따라서 적절하게 선택을 하셔야 된다라는 점으로 한번 정리를 해볼 수 있을 것 같고요. 두 번째 주제는 프로브에 대한 특성화였습니다. 그래서 이 웨비나에서 주로 말씀했던 거는 뭐 여러 가지 방법이 있었지만 2x 스루를 사용하는 방법, 혹은 뭐 PCB 끝단을 오픈이나 쇼트의 환경만 만들어주면 비교적 간단한 방법으로 프로브 끝단까지 특성화가 가능하다라는 부분이 있었고요. 더 나아가서 프로브 방식으로 측정을 할 때 프로브가 패드에 접촉되는 점에서 일어나는 불연속성, 이런 것도 간단한 방법으로 디임베딩을 같이 했던 그런 사례로 소개를 해드렸다고 정리를 해볼 수 있을 것 같습니다.
예, 디임베딩이라고 하는 과정 자체가 이제 뭐 특히나 어떤 오류를 제거할 수 있는, 혹은 측정에서 어떤 우리가 원하지 않는 어떤 내용들을 제거하는 어떤 방법으로서 적용할 수 있는 내용들이 될 것 같다라는 생각이 들고요. 오늘 그 질문도 꽤 많이 올려주셨어요. 그래서 지금 여기 임종택님부터 해서 쭉 이제 질문들을 올려주셨는데요. 우선 그 임종택님께서 질문해주신 내용이 생성형 AI 등을 연계하는 어떤 방안들에 대해서 문의를 해주셨는데요. 뭐 사실 오늘 보셨던 이 측정에서는 직접 AI가 관여가 되어 있다든지 그렇지는 않습니다. 하지만 측정 결과의 어떤 정리라든지 혹은 어떤 통계화라든지 이런 부분에서는 저희도 어떤 AI와 같은 어떤 기법들이 적용되고 있는 부분들을 저희가 확인할 수가 있기 때문에 이런 부분들은 어떤 그 현업에서의 과제 내용에 따라서 충분히 또 적용하실 수 있는 어떤 그런 혜택을 보실 수 있는 이런 부분도 되지 않을까라고 생각이 들고요. 이재현 매니저님, 그 질문이 꽤 많이 올라왔는데 어떻게 좀 답변을 좀 부탁드릴 수 있을까요? 시간이 좀 얼마 안 남았습니다만은 조금 답변을 해주실 수 있는 거 좀 봐주시는 게 좋을 것 같습니다.
네, 최대한 많이 답변을 드리기 위해서 좀 간략하게 설명을 드릴 거고요. 우선 첫 번째 질문은 임피던스 디임베딩이라는 의미가 나쁜 조건에서는 임피던스 바뀔 수도 있다는 건지요에 대한 답을 뭐 질문이 조금 명확하진 않지만 제 스스로 좀 해석을 해보자면 어쨌든 쿠폰이라는 거를 설계하셔서 별도로 그걸 이용하셔서 디임베딩을 진행하시는 거기 때문에 앞서 웨비나 내용에도 있었긴 했지만 실제 저희가 DUT가 포함된 픽처를 측정을 할 때 이 픽처와 쿠폰이 100% 동일한 실효는 아니기 때문에 물리적으로 어느 정도 다른 점이 있을 겁니다. 그래서 거기에서 일어나는 임피던스의 다른 점도 있을 거고요. 그래서 쿠폰을 이용해서 전통적인 디엠비딩 방식은 쿠폰만을 측정하셔서 실제 내가 픽처를 측정했을 때 그 쿠폰 값을 단순히 빼주는 그런 방식을 사용을 했었는데 최근에 제공되는 기능은 임피던스 코렉션 방식이라고 해서 픽처, DUT가 포함된 픽처도 같이 측정을 합니다. 그래서 쿠폰과 텍스트 픽처를 비교를 해서 픽처의 리드인 리드아웃 부분만 별도 수학적 알고리즘으로 제거를 하는 그런 좀 어드밴스드한 기능을 더 제공하고 있다. 이렇게 답변을 드릴 수 있을 것 같고요. 그 다음에 라즈베리 파이나 교육용으로 키트화에서 제공하는 게 있냐 이렇게 질문하신 것도 있는데 저희가 이런 디임베딩 관련돼서는 자체적으로 가지고 있는 테스트 보드가 있기 때문에 혹시 좀 더 뭐 데모가 필요하시거나 이런 게 필요하시면 요청을 주시면 저희가 가지고 있는 데모 보드로 별도로 소개를 해드릴 수 있을 것 같습니다. 네, 그래서 조금 한 2가지 정도만 더 보면요. 네, 현이님께서 PCB에서 소켓까지 디임베딩 적용 시에 DUT가 없는 상태에서 PCB에서 소켓 엔드 단까지 아마 오픈이 되어 있는 상태로 의미를 써주신 것 같고요. 그 다음에 뭐 툴에서 돌려서 계산된 S21 값으로 추출, 그 다음에 소켓을 제거한 상태에서 DUT 입출력을 각각 1x 리플렉션을 적용하지 않고 2x 룰을 대체해서 절반 값을 취한 뒤 S1 계산, 뭐 이런 해석이 맞느냐고 이렇게 질문 주셨는데 제가 이해하기로는 1x 오픈이나 쇼트 값을 가지고 별도 그 시뮬레이션 툴이나 디임베딩 툴에서 2x 수루로 변환을 해서 그거를 적용했을 때의 그 경우를 설명해 주신 것 같아요. 그래서 이러한 케이스로도 쓰실 수는 있고요. 2x 수루로 쓰셔도 뭐 더 정확한 방법으로 할 수도 있고요. 요것들은 그 뭐 소켓이나 혹은 픽처에 대한 다양한 형태나 혹은 테스트 조건에 따라서 많이 달라질 수가 있기 때문에 조금 주파수 범위라든가 혹은 형태라든가 이런 정보가 더 있으면 자세하게 가이드가 더 가능할 것 같습니다. 그리고 마지막으로 이유성님께서 질문해 주신 부분은 측정 시 과도한 힘을 가할 시에 프로브가 손상이 되는 경우가 있는데요. 이때는 어느 정도 힘을 가해야 하는지, 사실 요거는 뭐 프로브 형태에 따라서 다양한 조건이 가능한데 뭐 핸디형 프로브, 뭐 힘으로 실제 사람의 힘으로 누르는 핸디형 프로브도 있고 혹은 프로브 스테이션이라고 해서 기계적으로 일정한 힘을 가해주는 그런 프로브 스테이션도 있습니다. 그래서 일반적으로 프로브가 프로브 팁이 앞에다 달려있고 프로브 팁이 제품에 따라서는 뭐 가해진 힘에 따라서 팁이 부러지는 경우도 있고 손상되는 경우도 있기 때문에 제일 좋은 거는 기계적인 힘, 프로브 스테이션을 이용하셔가지고 일정한 힘으로 측정하시고 하시는 게 제일 정확하다라는 부분이 되겠고요. 핸디형 프로브를 사용하실 때는 항상 이런 부분이 문제가 될 수가 있습니다. 그래서 엔지니어들의 숙련도에 따라서 조금 많이 좀 달라지는 부분이라고 할 수가 있겠습니다. 네, 뭐 시간 관계상 이 정도까지 질문에 답 드릴 수 있을 것 같습니다.
예, 저희가 지금 시간이 조금 좀 더 지나가가지고요. 오늘 그 웨비나에서 지금 다른 질문도 꽤 많이 올려주셨는데요. 이 부분들은 또 저희가 추후에 개별적으로 또 답변을 드려야 될 것 같습니다. 그래서 이런 부분들 좀 더 양해를 좀 부탁을 드리고요. 참고로 오늘 웨비나에서 여러분들께 소개해드린 이 셋업은 그 10월 25일부터 열리는 그 반도체 대전 전시회에서 또 저희가 저희 로데 슈바르즈가 부스를 준비를 합니다. 그래서 이쪽에서도 또 여러분들께 보여드릴 수 있는 부분이 있기 때문에 아마 오늘 내용에 대해서 관심 있으신 분들께서는 그런 그 실제 전시회를 통해서 또 여러분들 한번 또 직접 보시고 어떻게 돌아가는지 좀 더 좀 자세한 어떤 인사이트를 얻으실 수 있는 그런 좋은 기회가 될 것 같아서 이 기회를 빌어서 다시 한번 여러분들께 그 행사에 대한 내용을 말씀을 드리고요. 오늘 지금 추석 이틀 앞두고 진행된 저희 웨비나에 꽤 많은 분들께서 또 참석을 해주셔가지고요. 다시 한번 여러분들께 감사를 드립니다. 저희들은 오늘 준비한 내용들은 이 정도로 일단 정리를 해야 될 것 같고요. 또 여러분들 명절 즐겁게 또 풍성한 한가위 보내시길 바라며 또 다음번에 또 더 풍성한 내용으로 또 저희 웨비나를 준비해서 여러분들께 찾아뵙도록 하겠습니다. 오늘 저희 준비한 웨비나 여기서 정리하도록 하겠습니다. 오늘 참석해 주신 여러분들께 다시 한번 감사드립니다. 고맙습니다.